there. Okay, friends. Your tests are almost done. I have one to pick up today. They'll be posted tonight. You guys did really well, but the other class beat you. And it's probably because you guys will not speak to me because I don't know what happened in our relationship, but it's really on the rocks. Yeah, it is you. I wanted to talk to you about that. We were going to have an intervention. But you all did well. Yeah. I can't because I still, there's tests that I have to pick up, and so I don't know what your actual average is yet. It was good. It was almost a B.
Almost a B?
Uh-huh. That's like, this is the first semester that I've actually gotten B averages, which is unheard of in anatomy and physiology. But no, they actually told me to do things to increase retention, and I'm like, I'm going to do it, but I'm doing it really well because I'm a boss. So I was like, am I going to get in trouble if their averages are really high? And she said no. I mean, I told her that in front of her boss, and she's just like rolled her eyes at me. I was like, yeah, oh, I can do it. Don't you think I can't do it? I can do it. And apparently other physiology classes, half the students have dropped, and I have lost two. So stick with me, and let's work on our relationship. Because our communication, not so great. Okay, thank you. All right, so it's. I mean, I do a lot of communicating. I feel like I'm carrying this relationship. More caffeine. I think I need more caffeine. Okay. So here's what we're doing today. We're doing cardiovascular system, which usually only gets 2 days. They are 2 rush days.
What?
Yeah. You guys are doing cardiovascular system last week in lab, and you're doing this week in lab, and there's going to be a lot of overlap between the stuff we're doing in lecture and lab, which is why I flipped it. Usually this week I do endocrine system, but I wanted to be better about being with lab, so hopefully that will help. It does when it happens? Okay. So I'm working on it. I think lab's in the wrong order, honestly. So I want them to change to me, and everybody else is like, they don't know all about you, and I'm like, okay. So, but here's the bad part. The bad part is that you actually need spring break to start thinking about endocrine, because endocrine, in addition to understanding the physiology, yes. In addition to understanding the physiology, you have, I think, 32 hormones to memorize, where they come from, abbreviations, alternate names. No, I did not. I said not as much memorization. Names, abbreviations, alternate names, where they come from, where they go to, what their chemistry is, and the impact on the target cell, and a couple of disorders. You can do whatever the hell you want. However, what I'm going to do is I'm going to have some expectations for you guys over spring break. If you come back and you haven't done it, that's on you, because it's going to be hard to cram it and learn all the physiology. Does that make sense? So usually what I would be doing is teaching endocrine right now, but instead I'm going to say, hey, here's what I expect of you guys out of endocrine. It's going to be like understandable what you can do, and you will know where to get the information. Go ahead.
So is that updated version of the endocrine notes is going to be on soon then?
Oh, it's already been updated. I just have to tell you how to use it. That's all. Yeah, I updated it last semester. Okay, so we're going to do cardiovascular system today. Here's what I love about cardiovascular system, and here's what's complicated about cardiovascular system. Good part. Cardiovascular system is logical. It's plumbing, right? It's a pump and some plumbing, and there's some pressure that you have to deal with. It's relatively logical. In addition, most of you guys remember the anatomy of the cardiovascular system, at least basically, right? You remember the valves, you remember arteries versus veins, so the anatomical retention is there. If you suck at cardiovascular anatomy, you need to go fix that. Because my assumption will be that you're going to have the anatomy down well enough to talk about the physiology. But in my experience, most of you guys actually retain cardiovascular anatomy relatively well. Okay, so the bad part is that there are a million little logical relationships Like if this goes up, what happens to this? Does it go up or down? If this goes down, what happens to this? Does it go up or down? But the million little logical relationships will only make one big, understandable predictor if you understand each one of them before we move on. So if you don't understand what I say when I say, if this goes up, what will happen to this? And everybody else but you goes, that will go down. And you're like, what the hell's going on? You need to stop at that point, right? You need to raise your hand and ask, because probably somebody else has that question as well, right? So I know this is not the most vocal class, and I'm an introvert too, but I don't want you to let yourself get confused and let it go over you, right? So just ask, okay? All right. So we are going to start with the overall physiological design of the cardiovascular system. And I need to teach you one trump value in the cardiovascular system that overrides all others and supersedes all others. And that the ultimate function of the cardiovascular system is to ensure adequate blood flow to capillary beds. Now that sounds relatively logical, but what I want you to understand is even if, for instance, you had to compromise another function, like blood pressure regulation, in order to accomplish this one always wins. Because, of course, ensuring adequate blood flow to capillary beds means that you can do what process? Because you're breathing oxygen? Yeah, and you are screwed if you can't do cellular respiration. So the reason I'm telling you this is that sometimes counterintuitive things will occur. Like, for instance, you've got hypertension and you like ate a whole bunch of cheeseburgers and haven't exercised in the last 20 years, right? And you got clogged up blood vessels, right? Okay, that means your blood pressure is high, yeah? That means that you're compromising blood flow to capillary beds. And then what you're going to do with your heart is what? You're going to pump harder, which will, of course, raise your blood pressure when you're like, what the hell is going on? Your blood pressure is high and made it higher. It's because there is a trump value that you're going for. And it's ensuring adequate blood flow to capillary beds, right? So that is the overriding homeostasis that you're heading for, even if it trashes the entire rest of the system. Because if it trashes the entire rest of the system, you were going to die anyway if you didn't ensure adequate blood flow to capillary beds, right? So that one wins, right? And if you ever get confused in the middle of the notes, you're like, I don't understand why the hell you're doing this. Look at that. That's probably going to be the answer. Okay, so what we're going to do is we're going to talk about the reasons that blood flows today, and then we're going to start talking about how the cardiac muscle works. Okay, so first thing is that this is plumbing, and blood will flow, any fluid will flow, due to pressure. And of course, the pressure is primarily created by the pumping of the heart, yes? But it can be augmented by two other things. Pressure is created by the pumping of the heart, but can't it be impacted by the diameter of the tubes? Yes? Or the volume of fluid in the system? Yes? Okay, so we will reinforce that multiple times. It's very frequent that you have to manipulate pressure, and there are only three ways of doing it. What the pump is doing, what the tubes are doing, and the volume of fluid in the system. Does that make sense? Got it? Okay, I need some feedback. Do you got it? Yes, good. Okay, so you guys start predicting, and we'll see if you're going to predict it. If you don't predict it, we'll fix it later. So what's your prediction? As pressure increases, flow tends to do what? Increase. Yes. Flow tends to increase as pressure increases. Now, is there such a thing as too high a pressure to have flow? Like, is there too much pressure that can actually blow out the tubes? Yeah, right? Like an aneurysm, yeah? So within normal ranges, typically, higher pressure means better flow, right? So if you turn on your the spigot to your hose, right, a little bit, then you get a little bit of pressure and a little bit of flow. Turn it on more, you get more pressure, more flow, right? What?
So kinking the hose.
We'll kink the hose in a minute. We'll talk about kinking the hose. Okay, so flow is opposed by, and this is something you may have never considered, flow is opposed by what's called resistance. And resistance is really what's happening in the tubes, the friction in the tubes, right? Resistance doesn't really occur in the heart because it's wide open and there's very little resistance and friction in the heart. So flow is opposed by resistance, and we'll talk about the factors that add to resistance, but I can give you a little bit of one. Where is there more resistance, in the big tube or a little tube? Little tube, exactly. So as resistance increases, flow tends to do what? Decrease, good. So resistance occurs primarily in the vessels, not in the heart. The heart's nice and wide. Okay, so we'll come back to the flow and resistance. So why the hell is it such a big deal that you need to get adequate blood flow in capillary goods? Because of course they are the only tubes that are thin and branched enough for adequate exchange, right? So all gas and nutrient exchange to speak of happens at the capillaries. And generally, if you're talking about systemic capillaries, what they're doing is bringing oxygen and nutrients and picking up carbon dioxide and waste products. Now, why can I pretty much guarantee that in systemic circulation, the tissues are going to have low levels of oxygen and high levels of carbon dioxide? In systemic circulation, when I get to the tissues, why can I pretty much guarantee that the tissues, what? Go ahead.
The organs have priority first, so if you're not getting enough oxygen in, it's not going to get to the tissue.
Okay, but what I'm asking is what is the reason that you can pretty much depend on your tissues having low oxygen, high carbon dioxide? Go ahead. Cellular respiration. It's all the same damn story, guys. Okay, so what happens is we don't really have to worry about transport because we've got a very dependable concentration gradient for oxygen, right? Systemic arteries are bringing in high oxygen blood, and systemic tissues are going to be low in oxygen because they've been working their little butts off, yes? And oxygen is lipid soluble, it moves straight in, yes? They're going to have relatively dependable high carbon dioxide because, again, they've been working their butts off. And you brought in low carbon dioxide blood. Carbon dioxide is going to diffuse straight out. So luckily, you don't have to worry about transport very much if you've got a dependable concentration gradient and good solubility. Does that make sense? Okay, so oxygen and nutrients are generally going to move by diffusion. A little bit of stuff is also pushed out by filtration, and some water gets pushed out by filtration. What if it's not oxygen or carbon dioxide? If you need to transport it into the tissues, there's generally a transport mechanism, like for glucose or something. What about leaked water? Because capillaries are all at least a little bit porous, and you always leak water from a capillary into the interstitial fluid. You don't pull it back up by filtration. You pull it back up by osmosis. Yeah? And so what that means is you've always got turnover of interstitial fluid, right? The interstitial fluid is being pushed out by filtration, pulled back up by osmosis, pushed out by filtration, pulled back up by osmosis. Does that make sense? Okay. So the rest of it, if it doesn't get picked up by osmosis, it gets picked up by the lymphatic system and dumped back into the subclavian veins. Okay, so now let's get into the logic of the system. You ready? Okay, so you're going to learn a couple of equations today. They're easy because they are just little logical relationships. Okay. First thing is that we are going to start talking about flow, which of course we said was the ultimate job of the system, right? So we're going to look at this equation, which is F equals delta P over R. F is flow. It's measured in some unit of volume per some unit of time, liters per minute or something, or milliliters per minute, or whatever the hell you want to measure. P is pressure, but notice that we're looking at delta P. We'll talk about that one in just a second. And R is resistance, okay? So things that we've already talked about. So I want to talk to you guys about that real quick. So what we're really saying here is flow is going to be directly proportional, not to pressure, but to delta P, which is the difference in pressure between 2 points. And this is going to be logical to you guys. Just think about plumbing for a second. So pressure is, of course, measured in millimeters of mercury, whether it's barometric pressure or blood pressure. So if I have a tube, right, a blood vessel, and I'm going to measure the pressure at point 1 and the pressure at point 2, and I say this one is 100 millimeters of mercury. And what if this one is 100 millimeters of mercury? Do I have any flow? No, right. So you guys already intuitively know that it's really not the pressure, the difference in pressure between 2 points, right? So if I change this one, yes, and I change this one just to 99, I know the directionality of flow, right? But it's not going to be fast, is it? No, there's no big delta P, so the F isn't going to be big. You with me? Okay. Now what if I change it to 70? Right? So the delta P predicts not only the speed of flow ultimately, but definitely the directionality of flow. You can tell which direction things are going to flow. Does that make sense to you guys? So it's just plumbing. So really what is true is not what you guys said before, but just a little bit more complicated statement, which is it's the difference in pressure between 2 points that determines both the direction and the speed or velocity of flow. Go ahead, Yuenta.
So is this like taking someone's blood pressure kind of thing?
It is, but hold that question for just a second and I'll bring in the blood pressure for just a second. It's going to take me a second to get to that. You with me? Okay? Everybody buy that you can look at this situation and figure out the direction of flow, yes, and that not measuring it yet because we haven't looked at resistance yet, but you can tell that it would actually have a faster speed if this was 70 than if this was 99. Yes? Go ahead.
So I can understand the math differential part of it, but if it's both at 100, why is there no flow?
Because there's no pressure differential. Let me show you a visual on that one. Ready? Okay. So this one, stick with me for a second. They set the resistance at a constant 2, and they just manipulated the delta P, okay? Don't worry about the resistance yet. Just know that it doesn't change in these 3 examples. You with me? Okay. So please look here. I have 100 millimeters of mercury over here. I've got 60 millimeters of mercury, which gives me a delta P of 40. The resistance was 2. It can't be 0, right? Otherwise, the math won't work. Got it? Okay. And so that gives me a flow of 20 mils per minute. You with me? Okay. But here's what I want to reinforce to you. It's the delta P that matters. It's not the P. Because if, for instance, somebody had to deal with hypertension and their blood pressure was way higher, what would happen is you could end up with the same delta P at much higher pressures. So let's look at this one, and then we'll look at this one. So this was Charles's question. So this, the delta P is 0, right? I held the resistance constant and I get 0 flow because there's no difference, right? Right. It's basically like, okay, if I sit a tube in a stagnant, like a sink of water, right? There's no flow through the tube because there's no pressure differential between the 2 sides. Does that make sense? It's not going to be going one way or the other. There's no pressure differential. Got it? Okay. Oh, yeah. Yeah. Okay, so, and now I want you to look at this one. Ready for this one? Please note, okay, this one, 200 millimeters of mercury versus 160 millimeters of mercury. Notice I get the same delta P at way higher pressures here, yes? Which ends up with the same flow because, of course, I held the resistance constant. One of these 3 situations represents something like normal blood pressure and blood flow, and one of them represents hypertension. Top one is normal one, and the bottom one is hypertension. Let's talk about hypertension for just a second, and we'll talk about measuring blood pressure. So the deal here is that if you want unidirectional flow of blood and you want the flow to be constant, right? We're not changing the resistance in any of these situations. And a person starts getting hypertension because of Chick-fil-A and inactivity, whatever, right? Then what's going to happen, guys, is this number starts going up, right? Combination of vasoconstriction and arteriosclerosis means that this is 95. Yeah? So what happens in order to ensure adequate blood flow to capillary beds is you have to generate more pressure on this end to get the same flow, right? That's how hypertension occurs. Does that make sense? And why will you do that if the high pressure is terrible for the system? Because you have to ensure adequate blood flow to capillary beds. Does that make sense? Okay, so ready? All right. So that means that we are saying that flow is not directly proportional to pressure. It's directly proportional to the difference in pressure between 2 points. Or as pressure difference increases, flow does what? Flow increases. Yeah, good. Okay, so let's reiterate. 3 ways to tweak pressure. What are they? Pump, tubes, fluid. Okay, got it? Okay. Cardiac muscle contraction, blood volume changes, and vessel lumen diameter changes. Yes? Okay. You guys know that pressure is measured in millimeters of mercury. And let's look at what the pressure does through the system. So fluids like blood are going to flow from high pressure to low pressure. And if we want unidirectional flow through a circuit, and we do, right? We want stuff to go not backwards. We want it to go through our systemic circuit from heart all the way back to heart, okay? Then what we are going to have to guarantee is that my left ventricle has higher or lower pressure than my aorta. Left ventricle, higher. Aorta, higher than brachial artery, yes? Right? All arteries. All arteries higher than all arterioles. All arterioles higher than all capillaries. All capillaries higher than all veins, yes? The two lowest pressure veins in the systemic circuit should be which ones? Superior and inferior vena cava. And then, not surprisingly, the right atrium is almost 0 millimeters of mercury. Does that make sense? That's how you get unidirectional flow through a circuit, okay? This is showing you average pressure and what it does through the system, and then we'll come back to Uinta's question in just a second. Okay, average pressure through the system. Arteries, relatively high pressure, starts falling at arterioles, falls again at capillaries, falls further at venules, really, really low at veins. Anybody have any idea why the pressure is so low in veins? There's actually kind of 3 things. No, like what anatomically or physiologically makes the pressure really low. Lose fluid as you go through capillaries, that'll do it, right? Okay. Further away from the pump, yes. Diameter, and also there are about 3 times as many veins as there are arteries. So collectively, the pressure is low. Does that make sense? Got it? Okay, go ahead.
So you were saying that it's nearly 0 at the atrium?
Mm-hmm.
Does that make it function kind of as a vacuum? Like everything's just...
It is. It should. Yes. It's nearly 0 millimeters of mercury, and we want everything going back toward the atria. We have passive venous return back to both atria.
And then releases it, sucks the blood back.
Yeah.
And almost like how...
But it's not a huge suction because, of course, the superior and inferior vena cava are very close to that, right? So it's like a sequential vacuum, right? Right? It's not like 0 to 80. It's like 0 to 2.5 to 5.
When we breathe in, I always thought we were forcing air in, but you're just breathing more air.
Yeah, that's what you're doing. Yeah, we'll talk about that too. Okay, so briefly, let's just look at the pulmonary circuit. Let's look at the pulmonary circuit. You ready? The pulmonary circuit is, of course, lower pressure, but the same trend, and this is looking at averages. Okay, so I'm going to phrase this question as carefully as I can. Here's the question I asked the last one. See if you guys can come up with the answer to it. Shh. It's come up with the answer to this question, and that is the systemic circuit is way higher pressure, right, throughout the system. The average pressure in the systemic circuit is way higher than it is in the pulmonary circuit. So I'll go ahead and tell you the answer you're about to tell me. The reason it's okay to be this low pressure is because the heart and the lungs are right next to each other and you don't need high pressure, yes? Here's my question to you. What anatomically is responsible for the difference in the pressure between the 2 circuits? There is an anatomical difference that results in difference in pressure between the 2 circuits. Go ahead, Naomi. Yes! Yes. The thickness of the left ventricle is way, way thicker and stronger and generates a lot more pressure than the right ventricle. Does that make sense? Okay. All right. So now let's go to, so the average pressure we just looked at, but now let's look at not average pressure, but let's take a few more data points and look at what happens. The pressure is highest in the arteries, but it's also most variable in the arteries. So let's look here. Ready? So if you actually took a bunch of data points instead of an average, and this is just systemic circulation, what you would see is the pressure is highly variable in the arteries. It still has a pulse pressure up into the arterial end of a capillary bed, and then you completely lose your pulse pressure on the other side of it. So what would happen in your arteries, for instance, if you put your finger on either your radial artery, if you put your finger on your carotid artery right here, you can feel the pulse pressure go up. So let's talk about Uinta's question. What you are actually seeing here is this represents your systolic pressure immediately after ventricular contraction. The pressure in your arteries is very high then. This represents your diastolic pressure immediately before the next ventricular contraction. So it's super variable. So I want you to think about that. That means that whether you've ever done it or not, you can picture if I nicked an artery, how would the blood leave? Squirt, squirt, squirt. Nick a vein and it will go trickle, trickle, trickle. Yes. Does that make sense? Okay. So this is basically showing you about, this is like maybe 110/70. That looks like their blood pressure, right? Which is totally normal at rest. Everybody okay with that? Okay, and I'll talk about systolic and diastolic blood pressures again later. So how much good would it do you to measure systolic and diastolic pressure in a vein? No, you're not going to get anything. It's going to be unmeasurable in a vein. Yes? Okay. Okay. So now we will come back to pressure multiple times, but I want to talk about resistance now. And resistance is kind of easy to understand, although you may have never done it before. Resistance is how difficult it is for blood to flow between 2 points at a given delta P. Okay, so let's keep this at 70. Okay, I'm not going to mess with the delta P while I'm messing with the resistance because then I won't be able to figure out what's causing the changes, right? Okay, so I'm going to hold this constant. I'm going to mess with the resistance. So peripheral resistance, how difficult it is for blood to flow between 2 points at a constant pressure difference. So flow is inversely proportional to resistance, or as resistance increases, flow does what? Decreases. Flow is inversely proportional, right, to resistance. Or as resistance increases, flow does what? Decreases. Got it. Okay, so the primary determinant of resistance is friction. Anything that adds friction to the system between point 1 and point 2 will add to resistance and therefore decrease flow. You guys with me? So I want to think about a couple of different ways that you can add friction into the system or manipulate the friction in the system. First time, what I'm going to do is hold this distance constant. Of course, I'm going to hold the pressures constant because I said it was. But I'm going to increase the viscosity of the fluid, right? Like with a person who just did blood doping, their blood gets really viscous. They have so many red blood cells in it, or if they have leukemia or they're really super dehydrated, then their blood viscosity goes up. So what would happen is I want you to imagine that I'm actually taking point 1 and point 2. I'm generating 100 millimeters of mercury pressure and I'm blowing, right? Or you can pump, but I can blow to show you what's going to happen. First fluid I'm going to try to blow through the tube is going to be half and half, which is about the viscosity of blood, right? And then I'm going to try at the same pressure to blow maple syrup through. Would you be able to get it to flow at the same pressure if the resistance was higher? So, logic question, guys. If you needed the same flow because you have to ensure adequate blood flow to capillary beds, the resistance goes up, what has to happen to the pressure in the system? It has to go up as well, okay? So you can have perfectly healthy athletes who end up giving themselves a heart attack by blood doping because their blood becomes so viscous that they can't pump it adequately. Does that make sense? Okay, so that's the viscosity of your blood. Now, does your viscosity change really frequently? No. It can change in situations like after menstruating, the viscosity of a woman's blood will change. She tends to lose some tissue, some blood. Her blood volume will usually drop a little bit and the viscosity can change. You get really dehydrated, then you have less blood volume, but it's also more viscous because you lost the fluid out of it, right? Leukemia will really change the viscosity of your blood. You have way too many immature, right, blood cells in it. But most of the time, the viscosity of your blood is relatively constant. So it's not something that like is changing really dramatically.
I would even want to know the clinical.
If they're in your notes. If they're in your notes, yeah. And I would like you to be able to think through them if it's not memorization. Okay, so let's talk about the next one. Vessel length. Okay, this time what I'm going to do is longer and shorter tubes, keeping the pressure measurements constant though. Still 100 versus 70, right? But I'm going to try to blow the same fluid, yeah, half and half, through a tube that's this long or a tube that's this long. Does that make sense? Okay. Now, of course, every single time the fluid comes in contact with the wall of the tube, there's friction, right? Even if there's only a little friction, there is friction, and that adds to resistance. So longer tube, more friction, therefore more resistance, yeah? Therefore, if I could blow through the tube, right, when it was this long, would the same pressure get the same flow if the tube was 5 times longer? No. So this matters to all of us for a couple of reasons. Because your vessel length, of course, changes dramatically with the changing of your body size from birth to adulthood. But so does the size of your pump. So right, they pretty much cancel each other out in a healthy person, right? When it changes again is as an adult, it's going to have to change during pregnancy, isn't it? You gain anywhere between 25 and 100 pounds in pregnancy. I have a 5'1" friend who gains 100 pounds every single time she gets pregnant. It is the funniest damn thing. It's straight out of the Chocolate Factory, man. It's like Violet Beauregard. And I keep telling her, you know what causes babies? And she's like, I just love being pregnant. I'm like, I don't know why. Nothing fits. Even her nose swells. It's weird. Okay, so if you've got more tissue, you have to supply more tissue. You develop angiogenesis and more vessels going to it, right? So guys, what is generally true about pregnancy and blood pressure? Yeah, it goes up while you're pregnant. If all things being equal, after you're finished being pregnant and have recovered, it'll go right back down. Okay? Now, let's think about gaining weight. Because it's happened to all of us except him at some point in our life. We all have our crosses to bear. Okay, at some point in our life. So let's say you just decide that you are going to go super carb happy, because, you know, they are happiness pretty much. And then what's going to happen, so let's say not you, let's make it extreme. Let's say we've got a person who, because of eating habits, lack of exercise, depression, PCOS, I don't know what the hell the person has, but they gained 60 pounds over the course of 3 months. Okay. 20 pounds in 10 days. You did? That was some talent. What, was it all water weight? Did you just like pee it all out later? Okay. You were just puffy. Okay, so you gained 60 pounds over the course of 3 months. And then, so here's what happens, guys. When you gain weight, you actually need more vessels to deliver blood to that tissue. And so I want you to understand, even if no one ever explained it to you before, can you see why the physics of weight gain correlates directly to understandable higher blood pressure with weight gain? Do you see that? It's because it has to. Yes? It's because it has to. You actually have to generate more pressure to get the fluid through longer tubes. Does that make sense? Now, I am not saying that everyone who's a big person also has hypertension, because let's talk about a 6'8" athlete. They can counteract that by being really athletic because their blood vessels are nice and open, right? But if we're just talking about one person gaining 60 pounds over 3 months, then you can have a dependable and understandable increase in blood pressure, yes? Because you've got more tissue in the same person. So what is, of course, the doctor going to tell that person to do when they go in and they have slight hypertension? Yeah, lose weight, diet and exercise, because that is a simple mechanism to drop your blood pressure, and the mechanics, it's just physics. You will drop your blood pressure. Angiogenesis occurs, but you can actually shrink the vast majority of those vessels right back down, and you will lose the weight. Okay, so it changes with weight gain and changes with weight loss as well. So that's vessel length. Now, vessel diameter. Vessel diameter is the part that I want you guys to listen to really closely, because people get confused about this. The first part of it makes sense, but then the second part of it, people get confused. Okay, so the general trend is really easy. I'm not talking about vasoconstriction and vasodilation yet. I'm just talking about the inherent diameter of a tube. There's this tube versus this tube, okay? The general trend is a larger tube has less resistance, right? And therefore what flow? Greater flow. So if you compare the aorta to the brachial artery, it's going to have a larger diameter and less resistance, okay? There is an exception though. Like a stream has pretty fast flow, and if you get a wider stream, it might have really fast flow, but if you make it into a lake, you get no flow. Does that make sense? That would be like an aneurysm when you like busted the thing. Okay, so it's not infinitely larger, gets better flow. okay? Because infinitely larger will eventually compromise the pressure, okay? All right, the smaller tube, more resistance, what flow? Less flow. Okay, now let's talk about vasoconstriction and vasodilation. You ready? So with vasoconstriction and vasodilation, if you are doing regional vasoconstriction and vasodilation, meaning that you are going to do it in an arteriole before a capillary bed to control flow to that capillary bed, does that make sense? Regional, short-term vasoconstriction and vasodilation. So if the arterioles constrict before a capillary bed, it'll do what to the flow to that organ? Increase or decrease? Decrease flow to that organ. Yes? Constrict. Okay. If the arterioles dilate before a capillary bed, it'll do what to flow to that organ? Increase. But, okay, make sure you've digested that because I'm about to tell you something that everybody hates, but I want you to be able to think about it. And I don't want you to write it right here. Write it somewhere else because it's a different story. But here's another truth that is related and people hate. Ready? Sometimes vasoconstriction and vasodilation is less about resistance and more about pressure. Okay, stick with me. If, for instance, I have a massive, massive peanut allergy and I eat peanuts on accident, yes, what will happen in my body is massive vasodilation because of anaphylactic shock. You with me? Okay, yes? Okay. That compromises the pressure of my system and I'm not delivering adequate blood flow to capillary beds. Okay? So in that instance, I will do a systemic, body-wide thing to my vessels that would help. What would it be? Massive vasoconstriction everywhere. Yes? Do you see that what I just did is this time I vasoconstricted to manipulate pressure, but that was systemic vasoconstriction, and that's usually controlled either by hormones, right? Or, for instance, by massively released paracrine agents or something like that. It's not local, okay? Does that make sense? Or let's say that my blood pressure was so damn high I was about to blow a gasket, and I took a pill to drop my systemic blood pressure down. What would it do to my vessels? No, not constrict. Dilate. Okay, so I want to reinforce this again. If you are doing regional vasoconstriction and vasodilation, you're primarily messing with resistance. Yes? If you're doing it systemically, you're primarily aiming at what? Pressure. I mean, I know you're hitting resistance, but that's secondary. Yes? Does that make sense? Okay. Does that make sense to you guys? Okay. So remember, whenever you talked about vasoconstriction and vasodilation, note to self, look for the words regional or systemic. Okay? Yeah? I will clarify. You just have to read it. Okay? Regional or systemic. Everybody understand that?
So it's safe to say that region, if it's constricted, it's controlling resistance.
It's controlling resistance and it will decrease flow.
Decrease flow.
Yeah?
But
If it's systemic, it's controlling pressure and it's going to increase flow. Does that make sense? Okay. All right. So now, we said that basically when you're talking about resistance, you've got viscosity, you've got vessel length, and you've got vessel diameter. But there's only one of those that you really manipulate. Which one? Vessel diameter, right? The other two change over time, or maybe with patho situations, but you don't like to tweak them all the time. So when you're trying to mess with resistance, you usually use vasoconstriction and vasodilation is what you're doing. You don't really mess with the other two. Okay, you guys ready to switch gears to cardiac muscle tissue? Okay, so now we are going to move to cardiac muscle tissue, and you guys are going to compare and contrast action potentials and contractions between skeletal muscle and cardiac muscle. And it's actually relatively easy because you just learned skeletal muscle contraction really well, right? Okay, so first thing before we actually get into the meat of it is that I want to tell you a couple things that you may or may not know about cardiac muscle tissue. First, that some cardiac muscle cells actually act as endocrine cells. Your heart actually releases a hormone, but I want you guys to do the predicting. You ready? Most hormones, this one included, are going with a negative feedback to maintain homeostasis prediction, okay? So some cardiac muscle cells secrete a hormone called atrial, that's where it's from, natriuretic which implies where it's going. Where? Natriuretic kidneys, okay? Peptide or factor, ANP or ANF. Textbooks can't decide which one they want to use. Okay, so I'm going to tell you why it's released, and you're going to try to predict what it does, okay? Ready? So this will give you some practice for hormones that are next. So it is released in response to prolonged atrial wall stretching. And prolonged atrial wall stretching might be an indication of what about your blood pressure? High blood pressure. Okay. It is released in response to prolonged atrial wall stretching because lots of fluid will stretch everything. Yeah? Okay. So prolonged atrial wall stretching. And it targets the kidney. And you guys tell me what you think it targets the kidney and makes it do. Do you think it has a diuretic effect or an anti-diuretic effect? Diuretic effect. So it's going to try to do what to your blood pressure? Decrease your blood pressure. That makes sense? It's going to make you pee it out. Good? Okay. Now I'm going to give you a little predictor. Just I want you guys to get into the habit of thinking this way. When we start running into hormones, and we're going to run into them a lot, you know hormones can have multiple targets because they're in the bloodstream, yes? Okay. So if a hormone is controlling blood pressure and it targets the kidneys to have a diuretic effect, it's never going to contradict that effect at another target organ. So you guys tell me, what is the only logical thing that ANP or ANF could do to the vessels? Sit there and think about it. So what's it trying to accomplish to your blood pressure? It's trying to decrease your blood pressure. And now I'm going to ask you again, what's the only logical thing that it could do to your vessels? Dilate. Yes, it's a vasodilator. Does that make sense? It'll drop your pressure. Okay, now I want to do another little pseudo example for you here. You ready? So, go ahead.
So was that a systemic example?
Yeah, it's totally. Hormones are systemic, aren't they?
Right.
Hormones go body-wise. Yes?
So,
Totally systemic example. Yes.
so okay, dilating decreased. Okay.
Okay, so let's do another one.
System constriction increases blood pressure.
Systemic constriction would increase blood pressure. Let's do a systemic example. You ready? Okay. It's actually one that you know, you just don't specifically know it as a hormone or like know everything that it does, but I bet you can predict it. Okay. Epinephrine, also called adrenaline, when released as a hormone, into the bloodstream, targets the heart and targets the vessels. You know what it's going to do to your blood pressure collectively, right? No. Epi. Sympathetic. Sympathetic nervous system does what to your blood pressure? Increases your blood pressure. So, I thought you said decrease.
I said increase.
Sorry, I thought you said decrease. Well, I was testing you. You did great. Okay, so here. Now I want you to tell me what it does to the heart. Increase or decrease contraction? Increase. What is consistent that it would do to the vessels? Constriction or dilation? No. Constriction. Yes. Yeah. It's increasing pressure in the entire system. Yes, and increasing the flow in the entire system. That's why in Pulp Fiction, right, which took too many drogas and went into shock. You never seen Pulp Fiction? It's a generational thing, man. Go see Pulp Fiction.
I know it's Quentin Tarantino, isn't it?
It's Quentin Tarantino. There's lots of death. There's some really good monologues by Samuel L. Jackson. I really respect those monologues. But epi, don't have to go straight into the heart. Epi straight into the heart because her blood pressure was really dropping. And what it did is increase her cardiac muscle contraction and vasoconstricted. Right? So the lesson I'm trying to tell you is that when we get to hormones, which all are going to behave systemically, right? Because they go, they go everywhere. If you know one thing that a hormone does for blood pressure, you can figure out what it does to the other organs, right? Like you would never cause vasodilation and an anti-diuretic effect, right? No, that wouldn't make sense. Yeah? If you had a diuretic effect, specifically, if you had a diuretic effect, the only consistent thing that you could do to the heart would be what? Decrease cardiac muscle contraction. Does that make sense? So remember that there's only 3 ways to tweak pressure, and what it does one place, it's never going to undo the other place. right? Okay? It'll be fine. You'll get it. You'll get it. It's fine. It's part of vascular system. You get it.
A lot of
Okay.
changes of flow and everything like that.
I know. I've got a big cardiovascular concept map that I'm going to post for you. But it will make you cry if I show it to you today, so I'll show it to you next time. Okay? Okay, ready? What? What'd you say? Oh, it might be the bad kind of cry, though. You're going to release, what was it? Oh, ACTH, adrenocorticotropic hormone. for sad cries. Okay, so let's talk a little bit, just briefly about metabolism in cardiac muscle cells. Cardiac muscle cells are not at all picky about nutrients. They will burn almost any sugar. They like glucose because everybody likes glucose. She's the hot girl. They also like fatty acids. See, they're equal opportunity. They also like lactic acid, almost any damn thing. But what they can't do is do any appreciable amount of anaerobic cellular respiration. So they're really dependent on a regular supply of oxygen. Okay, so they will get pissed off if you don't give them oxygen. They call that intolerance of ischemia, and ischemia is reduced blood flow. And so if your heart isn't getting enough oxygen, it's going to hurt. That's angina. And then if it really doesn't get enough, you're going to have a heart attack, which sucks because cardiac muscle cells are amitotic. So you don't want to kill them. Okay? All right. So now let's start talking about the activity in these cells. Okay. You have two different categories of cells in cardiac muscle. You have pacemaker cells, also called nodal cells, and they're in the SA node and the AV node and the AV bundle, left and right bundle branches, and Purkinje fibers, all of those like parts. These cells are not nervous tissue. They are cardiac muscle cells that lost their contractile proteins during embryonic development, so they're just specialized for action potentials but can't contract. Okay? So keep those in mind. And those are attached to their buddies by gap junctions, who are also attached to their buddies by gap junctions. You remember with cardiac muscle cells, gap junctions? They have intercalated discs with desmosomes and gap junctions in them, right? So they talk to each other, okay? So the other kind of cell you see has sarcomeres in it, and these are going to be called contractile cells. So you have the pacemaker cells and the contractile cells. You with me? So what we have to do is look at action potentials in both of them, and then contractions in one of them. Got it? Okay. Contractions are going to be super similar to the contractions that you learned before. So the pacemaker cells exist all throughout the heart, but they're clustered in a few places. SA node, AV node, the bundles, and the Purkinje fibers. There's also a few of them just scattered around that sometimes decide to launch a coup. Have you ever heard of an ectopic pacemaker, in which an area other than the SA node starts trying to take over? And they make your heart beat weird. They usually just go in and burn them off. Okay, so let's talk about the process of getting an action potential in our pacemaker cells. Okay, the pacemaker cells generate their own action potential. They have autorhythmicity. They have the ability to depolarize on their own. So I want to show you the graph for pacemaker cells. So these are your pacemaker cells, or nodal or autorhythmic cells. And what happens is they really never stay at their threshold for very long. It's like a variable threshold because they're always on their way to an action potential or recovering from one, because they're always about to have an action potential. And they do it on their own because what they have is a very dependable number of sodium leak channels, but they're not called leak channels, they're called funny channels. I don't know why. Because they're leak channels that under certain circumstances you can manipulate to behave differently, which makes them seem kind of like they're gated. Anyway, they call them funny channels, but imagine that they're leak channels. If you have a very dependable electrochemical gradient for sodium and a dependable number of these channels, then you can pretty much depend on the depolarization rate, right? Does that make sense? Okay. So what they're going to do is they are going to slowly depolarize to threshold. And threshold is between -40 and -50. So they're going to depolarize to threshold. Once you hit threshold, you'll involve some voltage-gated channels. It's going to be voltage-gated channels that you haven't met before, but they should be easy to understand. These are going to be fast, voltage-gated calcium channels. Would calcium also be depolarizing if it moved in? Yeah. It's a positive ion moving in. It would be depolarizing too. Does that make sense to you? Okay, so calcium would be depolarizing as well. The reason they're called fast is because we're going to meet slow ones in a minute. Okay, so right here is fast voltage-gated calcium channels. Go ahead, Charles.
Keep going.
Okay, so fast voltage-gated, they're not going to be in this picture. They're going to be in the next kind of cell. Okay, okay, so fast voltage-gated calcium channels are going to get you all the way up here. Okay, and you are going to basically be flooding the cell with some sodium and calcium, yes? Okay, so stick with me. How am I going to get back down to resting membrane potential again, guys? Open voltage-gated potassium channels, yes? Okay, same way you would always do it, okay? Open voltage-gated potassium channels and then do it all over again, okay? Over and over again. But please remember that what I'm going to do here is I'm going to flood myself with some sodium first and then some calcium, right? But then most of that sodium and calcium I'm not even going to keep in the cell because remember the entire job of these cells was to flood their neighbors, yes? So the vast majority of the sodium and the calcium that you brought in, you were actually going to send through gap junctions to depolarize your neighbors. Does that make sense? But whatever didn't go to my neighbors, I'm going to have to put back so that I can use this again, okay? So what I'm going to have to do is now I'm going to have to put everything that's left back where I got it, okay? So what kind of pumps are you going to need and where are you going to pump to? You need a sodium-potassium pump on the cell membrane pumping out, and you also need a calcium pump pumping out. That make sense? Okay, good? Okay, everybody good with that? Okay, so contraction does not follow in these cells. All they were doing is flooding themselves to hand it on to their neighbors, flooding themselves to hand it on to their neighbors, flooding themselves to hand it on to their neighbors. So let's do this. In this figure, you are going to do it again. Do this for me. You ready? Okay. What kind of channel is involved from here to here? From here to here.
Sodium leak channels.
Sodium leak channels or sodium funny channels. Yes. Got it? Okay. What kind of channel is involved from here to here? Fast voltage-gated calcium channels. What kind of channel is involved from here to here? Voltage-gated potassium channels. And there's two pumps that don't change the number, but you have to remember that they're involved, right? Sodium potassium pump and a calcium pump. Everybody good with that? Okay, so let's talk about some interesting things here. So you're at rest if you are otherwise healthy and your sodium concentration is relatively normal. What happens is this occurs about 100 times per minute. So your SA node is going to send out a flood of sodium and calcium to the contractile cells 100 times per minute. So at rest, if you yanked all the nerves off your heart would beat on its own without any innervation 100 beats per minute. Does that make sense? Yeah. Okay. So it would beat 100 beats per minute. So what happens is the rate can be changed with the dual innervation of the autonomic nervous system, yes? So let's reinforce what we've already learned. If I, for instance, do not want it to beat 100 times per minute, then I need to stick the brakes on it, yeah? With the which branch of the autonomic nervous system? Parasympathetic, releasing what neurotransmitter? Acetylcholine. Parasympathetic releasing acetylcholine would slightly hyperpolarize the cells and therefore make it so that you wouldn't hit it every single time. I'll show you the figure. So here it is with the parasympathetic nervous system added to it. Oh, sorry, parasympathetic nervous system is this one, blue one, right? You're slowing it down. All you have to do is, it's on its way to depolarization, just slightly hyperpolarize it and then it won't get there. It'll eventually get there, right? That's what's happening on your heart right now. Squirt, squirt, squirt acetylcholine, right? Because if you took your heart rate right now, it probably would not be 100 beats per minute. Does that make sense? So you have got your foot on the brake. You're wearing your damn brakes out all the time. But now if I get up to go to my car, right, all I need to do is take my foot off the brake, and that might make my heart rate go up enough to accomplish that. If somebody chased me into my car, I need to take my foot off the brake and put it on the gas, which is the sympathetic nervous system. When you put it on the sympathetic nervous system, you take a cell that was already on its way to a depolarization and you depolarize it, right? And you make it slightly faster, and then you get this green curve. Burp, burp, burp.
hyperpolarization of it is
The-
less or lower.
The hyperpolarization made it hit it slower, right? Because you were on your way and then you said, no, no.
With the sympathetic.
Sympathetic is depolarization.
It's depolarized.
Yeah, because you were already on your way to depolarization and you actually depolarized it slightly faster by adding what neurotransmitter, by the way? Norepinephrine. Got it? Okay, so sympathetic nervous system, parasympathetic nervous system cannot start or stop the whole pacemaker. It has to actually be done on its own. But after you start the car, you can work the gas or the brakes. Does that make sense? Okay. So have you ever seen anybody on TV? I'm sure you have, right? Clear and defibrillate. What are they trying to do? Are they trying to restart your heart?
Trying to stop it.
Yeah, they're trying to stop it. And then they wait. And what are they waiting for? They're waiting for this to kick back in because of the SA node. The SA node controls this. And we'll talk about the SA node a little bit more later. Is that okay? Are we good? Okay, so of course the next thing that we have to talk about is that now that we got the pacemaker cells going, they flooded themselves and then shared it with their neighbors. Now we got to get the neighbors to an action potential and then to a contraction, yes? So now what we are going to do is talk about the mechanism of contraction. They call it excitation-contraction coupling in cardiac muscle cells. And basically, this one's pretty easy because they were just sitting there doing nothing, and then they get flooded with sodium and calcium from a cell that brought in a whole bunch of it. So they go from nothing to an action potential really quickly. So let me show you that graph. The graph is really easy to tell the difference between that one and this one. Okay. This is an action potential in a contractile cardiac muscle cell. You go from a resting membrane potential of about -90 to pshum, all the way up, right? All the way up past 0. This kind of channel that will open because you got flooded, not from the extracellular fluid, but from your buddies, right? Is this depolarization occurs when you open a new kind of channel. And this kind of channel is a voltage-gated what? Sodium channel. This is a voltage-gated sodium channel, okay? You haven't seen these in cardiac muscle yet, okay, but you did see them in skeletal muscle. So let me just give you a visual of what's happening here, and we'll come back to this picture in just a second. This is pretty similar to your skeletal muscle picture that you looked at, but please note that it doesn't have a synapse because that's not how you start the contractile cells. You start them with their neighbors, right? So I'm going to flood through this gap junction, and if I hit threshold, I'm going to have an action potential that will go all the way down the T-tubules and cause what you expect to occur. Okay, and we'll talk about that in just a second, but let's finish the action potential first. Okay, so the action potential that occurs, so you get this big depolarizing stimulus from sodium and calcium coming through the gap junctions, and it's going to cause you to open fast voltage-gated sodium channels. You don't have to call them fast if you don't want to, but they occur before the slow ones, so you can if you want to. So you get an action potential, and it occurs on the sarcolemma, and it's going to do what you expect it to do. It's going to go across the sarcolemma and down the T-tubules, right? And then let's talk about what's going to occur. You ready? So this should be familiar to you. When it goes across the sarcolemma and down the T-tubules, it's going to cause what to be released from the SR? Calcium, which is going to bind to troponin and move tropomyosin, exactly. And then assuming that you have ATP and calcium present, you're going to start, right? Which is cross-bridge cycling, yes? Okay, so the same basic mechanism, right? In this striated tissue, you just started it with these rhythmic cells that you didn't have to control voluntarily. Okay, but there's one other thing to add to it. The original stimulus will also, as it's going across the cell membrane, open another kind of channel. And this channel right here is called a slow voltage-gated calcium channel. And what this is going to do, guys, is to allow calcium not just from the SR, but calcium from the extracellular fluid. More calcium means stronger or weaker contraction. Stronger. More calcium means longer or shorter contraction. Longer. Yes? I want you to think about that with your heart. Do you want your heart to do wimpy little contractions? No. You want it to do strong contractions. So if you're exercising, you want it to do stronger contractions, but you never want to half-ass it, right? You're like, want to do the whole thing. You want to do a good contraction, not like a teeny tiny little contraction. So I've got calcium from two sources. Lots of calcium means a longer, more sustained, stronger contraction. Does that make sense to you guys? In addition, it changes the look of the graph. Because what happens is this was a voltage-gated sodium channel, right? It tries to depolarize for just a second, and then the voltage-gated calcium channel opens right there and keeps you in your action potential for a longer time, a longer action potential, before it actually repolarizes. And this calcium is not only keeping you in your action potential, but it's also going into the sarcomere, right? That makes sense? And then, how do you think you're going to accomplish repolarization?
Potassium.
Opening potassium channels. Got it? Opening potassium channels. Got it? Okay, so the calcium from whatever source binds to troponin, allows sliding of actin and myosin as long as you've got ATP. And so then when you finish repolarization, in addition to opening and closing channels, you're going to have to put stuff back where you got it. Okay, so let's figure out what you need to put where. So let's look here. So what kind of pumps do I need and where in this situation? Okay, I'm going to need a calcium pump. There it is right there. I'm going to need 2 calcium pumps though, right? I'm going to need another one. I'm going to need one on the cell membrane, pumping it back to the extracellular fluid. And I'm going to need one on the SR. And then I'm going to need another kind of pump. Sodium-potassium pump. Although there is also a sodium-calcium pump. I won't test you guys on that one. There's a sodium-potassium pump.
Sodium is going into the cell, where sodium in the sodium-potassium pump, sodium is getting taken out.
Yeah, we don't talk about this one. Don't worry. You don't have to know that one. Sodium-potassium.
We don't talk about that's we don't talk
Yeah, that's special to cardiac muscle cells, and we're not going to talk about it. But the ones that you absolutely do know are 2 calcium pumps and a sodium-potassium pump, right? Sodium-potassium. Does that make sense? Do you actually have to memorize where to put those? You don't really have to memorize where to put those. Just put the stuff back where you got it, right? Does that make sense? All right, I'm all for not memorizing. I'm all for it. Sometimes it's necessary, but it's a necessary evil. Everybody okay with that? All right, so go ahead.
Why those ones do they not hyperpolarize? So like, on the normally it goes under the cystic. So like,
That is a really good question that I don't know the answer to. I will think about it and see if I can come up with it. I just never thought to ask that question before. She's like, why do you not slightly hyperpolarize when you're going back to rest? And I don't know. Like with this one, because this one does, right? This one always goes whoop, and then comes back up, but this one doesn't.
So polar already?
I don't know. I will look it up and see if I can figure out the answer.
Considered hyperpolarized?
Huh?
Maybe that's already considered.
Well, this is at rest, and it's right back to rest.
Well, it's depolarization is more dramatic.
Yeah, its depolarization is really dramatic, and its repolarization, I don't know. Maybe it's got to do with the number of potassium channels. I know I can figure it out, but the question literally never occurred to me before, so it's a good question. Huh? Maybe it's magic. No, that's never the answer. Go ahead.
So, with calcium being a positive 2 ion, does it depolarize?
It does impact,
faster?
yes.
Impact more so
Yeah,
than just
it does.
sodium?
Uh-huh.
And so
It
the
depolarizes faster.
Calcium's leaked in fast, it's just as fast like sodium is depolarized.
Depolarize. I don't know that it's twice as fast, but it's faster.
Okay.
Yes. Okay, so let's label. You ready? Okay. What is this channel, guys?
Sodium and calcium.
Voltage-gated sodium channel. Yes? And it's fast. I mean, there isn't a slow one in this story, but it's faster than the slow calcium that we're about to run into, right? So you can compare them to each other. Fast, and it is fast, right? Like, that's the fastest depolarization I have seen in any of these. So that's a fast voltage-gated sodium channel, although don't worry, you don't have to put fast in that one. But you do have to put slow or fast with the calcium ones because there's 2 different ones, right? So what's this right here? Slow voltage-gated calcium. And what's this? Voltage-gated potassium. Yes? Okay. So, interactive physiology, the missing disc, is phenomenal for cardiovascular system. And none of you guys have it, right? I have a feeling that I just need to like say, you could stick it under my door and I won't actually vilify you in class. But
We have 2 classes.
I've only got 2 phys
You've
classes.
announced in our class 3 times.
Yeah.
I wonder if they dropped the person who has it dropped.
That'd be jacked up.
I told the last class that I hope they drink sour milk in the next 2 days because that is really rude. I hope something terrible, but something they can overcome occurs to them, right? They've got the last bowl of Cinnamon Toast Crunch, and the milk comes out, and it's got chunks. That's what I hope for them. All right? You know how much that ruins your day. Have you ever almost cried because you're like, oh, my God? I also like, huh?
Turn it in, please. I want it too.
I don't have
I'll
it.
give it back to you.
I know you would. Next time I'll remember. I thought that we could depend on our fellow man. I should have known from the last election that is not true. I've become cynical. You ready? Okay, so here's the interesting thing about cardiac muscle versus skeletal muscle. With cardiac muscle, if we allowed the possibility of temporal summation, frequency stimulation, to get a stronger contraction, it would also leave open the possibility for tetanic contractions with cardiac muscle, right? So we do not want to add contraction to contraction. We want each contraction to be strong, right? And then we don't want the possibility for tetanic contraction. So the way that that's actually controlled in cardiac muscle cell is that the refractory period takes a really long time to reset the channels. So for comparison, the refractory period to get your voltage-gated channels reset in skeletal muscles is 1 to 2 milliseconds. In cardiac muscle, it's 250 milliseconds, which allows you plenty of time to like put the calcium back where you got it and all that kind of stuff. So by the time you have the capacity to have another action potential, you're not adding to the first one. Does that make sense? Very long absolute refractory period, therefore no tetanic contractions can occur in cardiac muscle. And in part that is because you never want your cardiac muscle to go into tetanic contractions. Relaxation is just as important as contraction with the heart. One of the reasons relaxation is just as important as contraction is that what's happening when relaxation is going on with the ventricles, for instance. They're filling up, exactly. So if they did this all the time and you get into ventricular tachycardia, then what's the issue? Well, the issue is that if you are not filling, you're not pumping, right? But then there's another issue that took me forever to understand, like an embarrassingly long time. Do you ever have those things that like bad song lyrics or like some scientific principle that like, oh my God, literally everybody understood the phases of the moon and I was 35 before I got it. This was like this. I was in graduate school before I figured out that like, okay, so I had this question. And you know sometimes that you like don't get it so you don't say it out loud. So this was my thing. I was like, I don't understand how if the heart's always full of blood, you can never have a heart attack because it's not getting enough blood. Well, you know, because I was your anatomy teacher, so shut your pie hole.
Well,
so, I mean that in the nicest possible way. Okay. So I got confused, and I was confused into graduate school. But give me a break. I was educated in Texas, so it's amazing that I got past high school. So what is happening is if you get into ventricular tachycardia, what's going on is this, it's going on too quickly. Okay, so the ventricles are contracting too quickly, and if the ventricles contract too quickly, you need to remember that of course you can't fill, but the other thing is that the relaxation, something else important is happening during relaxation other than filling, and that is that when your ventricles contract, just think about your left ventricle right here, or left ventricle for a second. So left ventricle contracts, it pushes blood, of course, into the aorta, and into the left and right pulmonary arteries if we're delivering blood to the heart, right? We all know that, even into the smaller arteries. But simultaneously, when it's contracting, it's also compressing the wall of the ventricle. So it's like sticking a sponge underwater and squishing it. Did you actually take up the water yet? No, you take up the water when you relax your hands. So when you actually push blood into your arteries, you're compressing your myocardial capillaries. Does that make sense? And so ventricular relaxation not only allows for the ventricles to fill, but it also allows for the muscle itself to get the blood. Does that make sense? So if you go into ventricular tachycardia, you're actually cutting off blood flow to the heart by compressing the capillaries. Go ahead.
Is this thing when it's skeletal muscle, so if you sit there and contract, you're basically constricting blood flow or not allowing blood flow to do the slow twitch?
No, because we have this thing with the heart that it's doing two different things. It's pushing blood into the arteries, right? Does that make sense? But it's pushing blood into the arteries, but the same thing that is pushing actually needs blood. with skeletal muscle, the heart is pushing blood to the skeletal muscles, and you're not limiting what the heart will do with the skeletal muscles. Does that make sense? So, yes, when they relax, they'll get a little better blood flow, but it's not the same kind of thing. Yeah, it's not the same kind of thing. Yeah.
More severe than that.
Yeah, way more severe. Okay, so, okay, everybody good? Okay, so the last thing that we're going to try to get to today is the concept of cardiac output. You ready? Cardiac output is also a really logical relationship, but it's another equation. And by the way, just because you see an equation doesn't mean it's math. It's just logic, right? I mean, you can put numbers in there, but if you understand the principles, you don't have to put numbers in there, okay? To me, I've always been really good at logic, but I hated math. So I told the last class that what I did was like, after I figured out that I knew how to do the problem and I proved it to myself like 3 times, there is no way in hell I was ever doing the other 70 problems. I was like, I just proved that I know how to do these. And my husband actually told me to stop helping my son with math the other day. He did. And Evan was like, okay, so it's just like this one, and this one's just like this one. I was like, why the hell do you need to do 15 of them then? You just did it twice. And Mike was like, Mel, why don't you go have a glass of wine? Which is why my trigonometry professor told me that I was going to be, quote, a burden to society. He did. Right after I flipped him off. He was a bastard. He was a bastard. He made us sit in high school. I was a sophomore in high school, I think. Hands on the desk, feet on the floor. Yes, sir, no, sir. I was like, I don't think that I am the right audience for you. Okay, so we're going to talk about cardiac output. Here's what cardiac output is, guys. Cardiac output is the amount of blood that is ejected from the ventricles per unit time. Doesn't matter what unit time you choose. Usually it's measured in liters per minute. It's always in volume per unit time. And it's really determined by 2 really logical factors. How many times you beat per unit time, right? Heart rate. Does that make sense? And how much you squirt out per beat. Does that make sense? Okay, totally logic. Okay, so the number of heartbeats per minute is your heart rate. The amount of blood that's ejected from a ventricle, we usually focus on the left, per minute is your stroke volume. Does that make sense? Okay, so cardiac output equals heart rate times stroke volume. Okay, so here's an adult example, guys. This is within normal. Within normal, a stroke volume could be around a 1/4 cup per beat, and a heart rate that would be within normal range would be around 72 beats per minute. I mean, there's a lot of variability, but that's within normal, right? Mm-hmm. And if you multiply that out, it ends up getting you about, rounding, about 5 liters per minute, which is kind of impressive because does anybody know how much blood you have?
7.
Only if you're enormous.
5, 6.
4 to 5 for most women, 5 to 6 for most men. Okay, depending on body size. It's not like your wiener gets any extra like liter of blood. It's just based on that. I mean, I know it feels like it does sometimes, but it's just based on body size. Those are averages. I'm so glad that's on tape.
It's not. We're not recording this.
Yeah, it is. I mean, I think it is. It's there.
All right, we're good.
Recording. I'm gonna have to erase that part. Okay. It's pointless. You guys all heard it. Okay. So around 5, and that's at rest, by the way. Of course, it can get way, way higher than that. And if you're Lance Armstrong, even before he started doing drugs, his stroke volume was around 3 times the normal stroke volume. 3/4 of a cup per squirt, which means what could happen to his heart rate and still maintain his cardiac output? 37 beats per minute at rest. He was a big freaking sloth, right? Does that make sense? Okay, so logic question before we go any further. You ready? Okay, cardiac output is directly correlated to one of those 3 factors. Which one?
Pressure.
Yeah, it's directly correlated to flow, and it's one of the generators of pressure. Yeah. So cardiac output generates pressure to make flow. Okay, does that make sense? Okay, ready? All right, so interactive physiology, again, phenomenal for the cardiovascular system, really, really, really good for cardiac output. So if this stuff starts getting confusing, and it will, let's start talking about cardiac output. So let's start talking about stroke volume first, because you already kind of know a lot of ways to manipulate heart rate. One of them is with the autonomic nervous system, right? There's also going to be some hormones that do it, some other stuff that do it. Okay, stroke volume is the one that's probably a little less intuitive for you. So let's start talking about at least one factor that will impact how much leaves the heart per ventricular squirt. You ready? This one I want you to listen to really carefully, because please remember that the heart is going to generate pressure, but it also has pressure that it pushes against, right? Arterial pressure that it pushes against. Okay, so afterload is the pressure that you are pushing against. Okay, afterload is the arterial pressure against which the ventricles must pump. Okay, so I want to think about two extreme examples, and you guys tell me the stroke volume. Lance Armstrong. His blood vessels are nice and wide because he did hours and hours of cardiovascular exercise per day, right? That means that his P2 would be really low, right? And therefore his stroke volume would be really high. Yes, that makes sense? Okay? So his stroke volume is super duper high. And then let's talk about my relatives in Texas, right? That probably smoke 2 packs a day, right? And ride the little thing around in Walmart, even though their legs work. 250 pounds, make you feel really good about yourself, right? Live on beer and fast food, right? Okay? So let me talk about their arteries. What do you imagine? Arteries constricted, gumped up, right? Whole bunch of Chick-fil-A in there. Actually, it's Kentucky Fried Chicken Churches down there. So Church's Fried Chicken, all gumped up. So their afterload is what? High or low? High, which means their stroke volume is going to be low. Exactly. Does that make sense? So afterload is the pressure that you're pushing against. So the arterial pressure against which the ventricles must pump. Increased arterial pressure tends to do what to stroke volume? Decrease stroke volume. Got it? Afterload increases and stroke volume decreases with high blood pressure, which is hypertension. Okay? What is a way that you can clean out your blood vessels, make them nice and clean, big, wide, and open, so that your afterload drops? Cardiovascular exercise. Go ahead.
So if the stroke volume saves a quarter cup before, like in the ventricle, and you squeeze it, when the quarter cup just come out?
It doesn't come out without a whole bunch of resistance is the problem.
Okay.
Yeah, right. So it's how much
So
is leaving.
the stroke volume is like how many beats or how many meters per?
It's still going to decrease. Imagine that the tube was smaller. Are you going to get out exactly the same amount every time? No, you're not. And eventually it's going to affect what comes back to the heart too. Oh, if you punched a hole in it. Okay. Okay, so I want to show you something that you're going to run into next time, just so you're ready for it. So this is afterload because it happens after the heart, yeah, and the arteries are after the heart. There's also preload, but that happens in the heart. Yes, preload has to do with how full the ventricles are before you contract them. Afterload has to do with what comes out of the heart into the arteries. Does that make sense? Okay, now, what would happen, by the way, Charles, is you would compensate. If you still needed the same flow and your stroke volume, so this is the real answer to your question. If your stroke volume went down because you were one of my redneck relatives, right? What would you have to do to maintain the same flow? You'd have to increase your heart rate, yeah. That's what would have to happen. You'd have to increase your heart rate to compensate, right? And that's what does happen, right? With hypertension, then your heart rate climbs up. That makes sense to you? Okay, so I will see you guys on Wednesday. Go ahead. Uh-huh. It's not usually over 100, but it can get into the 90s. Yeah, resting heart rate of 85 or 90, 95. When you're over the 80s. Yeah. Mm-hmm. I have to go pick that up.
Yes, I have, but where did that come
This would have been a really good day to attend both of you.
Marissa did.
And I did so we'll be watching so that quite often.
The cardiovascular system takes a minute to get down, but I'm going to post a video for you guys that goes through a concept map for the cardiovascular system.
You were.
And you haven't got all the terminology yet, so you've only got little pieces of it.
I know, I'm surprised when we get it all.
So far, the first half of this is
Most what?
most difficult. Just like action potentials and
Oh, yeah.
You've never tried to say that? You said that.
After you got that,
yeah, no, it's
I know
obviously
the action
critical.
potential part, or like the depolarizing. I'm like, yeah, that's easy.
I totally got that. You remember how hard you used to think that was?
Yeah.